An inductor is a very interesting device in that when you simply connect a DC power supply across it, it acts as a magnet. It has many applications across all engineering disciplines. Let's take a logical look at the physics behind inductors. A current-carrying conductor produces a magnetic field around it, as shown. Let's do an interesting experiment. Let's bend the wire. As you bend the wire, the magnetic field lines interact with each other and produce an interesting magnetic field pattern, as shown. This magnetic field pattern is similar to that of a permanent magnet, which is why a current-carrying loop acts like a permanent magnet. Clearly, simply by increasing the number of loops, we can increase the magnetic flux. We can also increase this magnetic flux by increasing the current through the coils. A constant called inductance connects between the magnetic flux and the current's value. The value of inductance depends purely on the geometry of the coil. Now, for the most important part of this video. What will happen if the current through the coil changes? When the current changes, the magnetic flux that the coil produces also changes, which means we need to study the effect of this varying magnetic flux on the coil. To study the effect of varying magnetic flux on a coil, we need to introduce Faraday's law. The great scientist Michael Faraday said if the magnetic flux changes across a loop, it will induce an EMF across it. Here you can see that the permanent magnet approaches or leaves the loop. It will induce an EMF across it. This result occurs because the movement of the permanent magnet causes a varying magnetic flux on the loop. Now, let's apply Faraday's law to an inductor connected across an AC power supply. According to Faraday's law, the varying magnetic flux that the AC power source produces will definitely produce an EMF across it. This EMF is known as back EMF, and this phenomenon is called self-induction. The electricity we use everywhere is sinusoidal in nature. It's therefore very important to study the effect of a sinusoidally varying EMF across the inductor. You might have noted that in Faraday's law, everything is about the rate of change. So let's study more about a sine curve's rate of change. Clearly, for the sine curve, the change is zero when the current is at the peak, and the change is maximal when the current is zero. This is one interesting property of a sine curve. The EMF it induces is proportional to the change in current. Therefore, the EMF across the inductor is zero when the current is at maximum, and the EMF is at maximum when the current is zero. In short, the back EMF will vary as shown. If the resistance of this circuit is negligible, the EMF induced across the inductor should be equal to the applied voltage, but opposite in sign. So the applied voltage also has the same variation with the current. When the applied voltage is maximal, the current through a pure inductor circuit will be zero, and when applied voltage is zero, the current flow through the circuit will be maximal. In short, when a sinusoidal voltage is applied across a pure inductive circuit, the current will lag the voltage by 90 degrees. This is a crazy behavior. However, using the fundamental laws of physics, we have explained the reason behind it. We hope you have developed a good conceptual understanding of inductors. Thank you.